Hello everyone. Today we are going to look at the electromagnetic waves, and this lesson is going to be a kind of presentation. It is because of the nature of the topic and the learning objectives for this lesson. You are going to be able to describe the sources of electromagnetic oscillations, and you are going to be able to understand the properties of electromagnetic waves, and then you are going to be able to familiar with the electromagnetic spectrum. What is an electromagnetic wave? They are made of vibrating electric charges. When an electric charge, think of a positive charge vibrating back and forth. When a charge, positive or negative, not important, if they are vibrating back and forth, the electromagnetic waves are produced, and they are traveling in space, and they are traveling by vibrating electric and magnetic fields. The sources of electromagnetic waves. How do we produce electromagnetic waves? The high-frequency electromagnetic waves are produced by atoms and nuclei, and they are called gamma rays. And intermediate frequencies are generated by heating and cooking, and they are called infrared rays. Low frequencies are produced by electric circuits, and they are called radio waves. And this is not all spectrum. I will explain it in the next slides. So all matter contains charged particles, that they are always moving. Therefore, all objects emit electromagnetic waves. Your pen, your desk, your body, they all contain electric charges, and they are all moving, accelerating. That's why they are all producing electromagnetic waves. What are the properties of the electromagnetic waves? First of all, for a mechanical wave, for example, for water waves, we need water. For sound waves, we need air. But for electromagnetic waves, we don't need any medium. They can propagate in empty space. And as I said, they are produced by oscillating electric charges. And they can be detected at great distances. For example, ultraviolet light is produced at sun, and we can observe them on the earth. The electromagnetic waves carry energy and momentum, and they cover many frequencies. I will explain it in the electromagnetic spectrum section. Let's continue with the properties of electromagnetic waves. And all electromagnetic waves travel in empty space with approximately 300,000 kilometers. And they usually travel slowly in solids, and their speed is decreased in gases also, but not as much as in solids. In empty space, it is about 300,000 kilometers. In air, it is less than this, and in water, it decreases to 226,000 kilometers per second. In glasses and in diamond, it decreases a little bit more, and it decreases to 124 kilometers per second. Let's look at some other properties of electromagnetic waves. When the electromagnetic wave is propagating, this is the direction of propagation. This is the direction of change of electric field. In the y direction, it is changing, and there is the change of magnetic field. This is the change of electric field, and this is the change of magnetic field. The blue colors represent the change of the magnetic field, and as you see, they are perpendicular to each other. I mean, the change of electric field is in the y direction, and the change of the magnetic field is in the x direction, and the propagation is in the z direction. So that's why, since the direction of propagation is perpendicular to the change of the electric and magnetic fields, it is a transverse wave. The magnitude of the electric and magnetic fields in empty space are connected with this formula. The speed of the light is equal to E over B. And the electromagnetic waves obey the superposition principle. That's why we have interference in electromagnetic waves. For example, the interference of light. I mean, the light waves can construct each other, they can destroy each other. It is because of the superposition principle. Let's continue with the properties. When an electric charge vibrates, the electric field around it changes, creating a changing magnetic field. So when an electric field is changing in this direction, a perpendicular magnetic field is created. Think of a positive charge. There is electric field around the positive charge like this. These are lines representing electric field. And so when this charge starts accelerating with an acceleration, then the electric field around is going to change, and a changing electric field produces a magnetic field. And once an electric field is changing and it creates a magnetic field, a changing electric field creates a magnetic field, and this changing magnetic field again creates an electric field, so they create each other again and again. That's why they are propagating. So electromagnetic waves travels in all directions. For example, when you light on your lamp, you see the lights from all directions, so they travel to all directions. So there are two key points to understand electromagnetic waves. An oscillating electric field generates an oscillating magnetic field, and an oscillating magnetic field generates an oscillating electric field. They generate each other and they travel in the space. So let's look at the discovery of the electromagnetic waves. The theoretical basis of the electromagnetic waves was founded by Maxwell's equations, but then later experimentally Hertz confirmed Maxwell's predictions, and in 1887 he discovered the electromagnetic waves. What was his experiment? Briefly, in the Hertz experiment, an induction coil is connected. There's an induction coil, something like this, is connected to a transmitter, and the transmitter consists of, this is the transmitter, it consists of two spherical electrodes separated by a narrow gap. There is some distance between them, and there are two spheres here. Then the coil provides short voltage surges to the electrodes. These are connected to some changing alternating current source, and the voltages are delivered to the spheres. So there's a potential difference between these two spheres, and the air ionized, and there is some jump of the electrons from the negative sphere to the positive plate, to the positive sphere. So as the air is ionized, as I said, the electrons are jumping from one sphere to the other one. So there is a discharging in this system, and this discharging has an oscillatory behavior. I mean, the voltage, the polarity of the voltage, I mean the polarity here, for example, initially it is positive, this is negative, then this is going to be positive, this is going to be negative, the polarity is going to change, so electrons are going to jump once to that side, and then once this sphere becomes negative and this one becomes positive, the electrons are going to jump to that direction. So as electrons are jumping from one sphere to here, to another sphere, the key point of the electromagnetic waves, as I said, was accelerating of the charges. When electrons are jumping from here to here, they accelerate. Why? Because this is positive and these are negative. There is attraction between them. Electrons are going to accelerate. Once they are accelerating, the electromagnetic waves are produced and they travel. Once they are traveling, there is a receiver. The receiver is also consists of two spheres. Once electromagnetic waves are reaching to this area, then some jumping of the electrons are observed here also. There is no circuit, there is no power supply in this receiver, just electromagnetic waves traveling in space are producing some effect in this receiver, and electrons start jumping from here to here again. And let's look at the basic principle of working of antennas. So when a charge is stationary, for example, positive charge V is equal to 0, or when a positive charge traveling with constant velocity, and no electromagnetic waves are produced. We need acceleration of charges for the production of the electromagnetic waves. Now here, two conducting rods are connected to an alternating source. As the source's polarity changes, these plates or these rods are charged positively, negatively. Then this is going to be positively charged, this is going to be negatively charged. So as the polarity of this rod and this rod is changing, the electric field lines are, as you see, electric field is produced from this plate to that plate, and since the charges on these rods are changing, this produced electric field is also changing. As I said, as I explained before, a changing electric field produces a magnetic field which is perpendicular to the electric field, and they are propagating in the empty space. Let's look at the spectrum of electromagnetic waves. So all frequencies of electromagnetic waves are called electromagnetic spectrum, and different parts of the electromagnetic spectrum interact with the matter in different ways. And the visible light is the light detected by human eye. and it makes a very small part of the whole spectrum. I will now show you the whole spectrum. So there is no sharp division between the one kind of electromagnetic wave to the next one. Okay. And the most important thing here is that all types of the electromagnetic spectrum are produced by by accelerating charges. Here is the electromagnetic spectrum, and as you see, electromagnetic spectrum changes frequencies changing from 10 to the 3 up to 10 to the 22, and the wavelengths are changing more than 1 kilometers up to 1 picometer. The frequency and wavelength are inversely proportional. That's why low frequency corresponds to a high wavelengths. And as you see, when the wavelengths are very high, we call them long waves, and radio waves also are long waves. And then we come to the microwaves. As you see, the wavelength is decreasing, and here we have infrared waves. Then between the ultraviolet and infrared rays, a very small portion of the electromagnetic spectrum, very narrow portion, makes the visible light, and this wavelength of the visible light changes from 400 nanometers up to 700 nanometers, and this is 700 nanometer corresponds to the red light, and this one corresponds to the violet light. So then we have X-rays and then gamma rays. So this type of the wavelengths, I mean this type of the electromagnetic waves, they are distinguished by their frequencies or by their wavelengths. Let's look at the radio waves, and their wavelengths changes from 0.1 meter up to 10 to the 4 meters, and we use the radio waves in radio and television communication systems. On the other hand, the microwaves have wavelengths ranging from 0.3 up to 10 to the negative 4 meters, and we use them in radar systems, and also we use them in microwave ovens. And infrared rays, they are produced by hot objects and molecules. And their wavelengths are ranging from 10 to the negative 3 up to 10 to the negative 7. The visible light, as I said, it is a very small portion of the electromagnetic spectrum, and it is the visible light is the spectrum part of the spectrum detected by the human eye, and human eye is most sensitive at 5.5 10 to the negative 7 meters, and this wavelength corresponds to yellow-green light. And ultraviolet light, as I said, the sun is an important source of ultraviolet light, and their wavelengths is ranging from 10 to the negative 7 up to 10 to the negative 10 meters. X-rays are produced when high energy electrons are striking a metal target. When they are striking the metals, they produce X-rays, and their wavelengths are also changing from 10 to the negative 8 up to 10 to the negative 12 meters. Finally, the gamma rays, they are emitted by radioactive nuclei, and this is their wavelengths. The formula that we are going to use for the problems maybe we solve in this topic, the C is equal to lambda f. C is the speed of the light in vacuum. It is equal to approximately 3 times 10 to the 8 meter per second. This is the frequency of the wave, and this is the wavelength of the wave. If you want to calculate the energy of an electromagnetic wave, you need to know its frequency, and you are going to multiply it with the Planck's constant. It is given here. Let's look at some examples. The first one, what is the frequency of green light that has a wavelength of 5.3 times 10 to the negative 3 meters? We know that what is the frequency? It asks the frequency. We know that F is equal to C over lambda, and it comes our formula. Remember, I told you that C is equal to lambda F. So here the speed of the wave is 10 to the 8, 3 times 10 to the 8 divided by 5.3 times 10 to the negative 7, and this will give us approximately 5.66 times 10 to the 14 hertz. Okay, let's look at the next question. Compare the properties of infrared and radio waves. Let's quickly go back to the spectrum and see. Here is electromagnetic spectrum. We are going to compare the radio waves. Their frequency is 10 to the 7, and to the infrared rays, their frequencies are ranging from 10 to the 11 up to 10 to the 12 hertz. And let's look at our questions. Okay, what type of waves are these? These are both infrared and radio waves are electromagnetic waves. Which has greater speed? Their speeds are equal to each other. All electromagnetic waves travel with the same speed. C is equal to approximately 3 times 10 to the 8 meters per second. Which has greater wavelength? The radio waves have greater wavelengths and they have smaller frequencies. Which one carry more energy? The energy depends on their frequencies. It is equal to HF, and the frequency of the infrared light is more than the frequency of the radio waves. That's why infrared lights carry more energy. Let's look at one more example. The average distance to the sun from the earth is 149 million kilometers. How long does it take light from the sun to reach earth? To calculate the time, we are going to use our simple formula d over v, distance divided by the velocity. We know the velocity, the distance is given 1.49 times 10 to the 11 meters. I mean, this one makes 1.49 times 10 to the 11 meters, divided by the speed of the light is approximately 3 times 10 to the 8, and this division will give us approximately 8.3 minutes. Okay, and it was approximately 497 seconds. So the last question, how many wavelengths of light of 5.5 times 10 to the 14 hertz fits across the width of your thumb? The width of our thumb is approximately 2 centimeters. Now first of all, let's calculate the wavelength. And the wavelength is equal to C over F from our previous formula. And it is equal to 3 times 10 to the 8 divided by 5.5 times 10 to the 14, and it will give us approximately 5.45 times 10 to the negative 7 meters. So this is the wavelength. So how many wavelengths are going to fit in 2 centimeters? So number of the wavelengths is going to be equal to 0.02. 2 centimeters is equal to 0.02 meters divided by the length of one wavelength. It is 5 times 45 times 10 to the negative 7 meters. So this will give us approximately 3.67 times 10 to the 4 wavelengths. Okay, this is it. Thank you for listening. See you next time.